All right. Hi, everybody. My name is Nate Johnson. I'm going to be talking to you today about DSTE, which is an application I work on. And we're going to be focusing a little bit, or mostly, on how DSTE has been utilizing FreeFlyer in its most recent release. So what is the problem that we were trying to solve when we made DSTE? What's our background here? A lot of our more recent and future missions are going to more complicated orbits than we have in the past. Orbits around our Lagrange points, Gateway and Artemis going to the Earth-Moon system, L2, James Webb going to the Sun-Earth system, Lagrange point 2. And although there are a lot of tools around like FreeFlyer that can analyze orbits and trajectories, once you have them, it can be hard to create these orbits or know how to create these orbits and create trajectories to these orbits. And that's kind of where DSTE comes in. So DSTE, if you haven't seen it before, is the Deep Space Trajectory Explorer. It's a Java-based software we make in-house here at AI Solutions. And kind of the focus of DSTE is to use Java's powerful visual effects to allow analysts to explore these large data spaces or design spaces, data sets, and be able to quickly parse through those and pick out what trajectories and orbits are going to be ideal for them. And another big focus is that DSTE is not only capable of parsing through these data sets, but also generating them on the fly for you. So I can come into DSTE and not know anything about how to create a near rectilinear halo orbit, but maybe I know that's what I want to look at, and DSTE can generate a variety of orbits like this. And so that's our big focus, is essentially allowing you to do this very quickly, get a lot of your engineering cycles in, even when you don't necessarily know exactly how to generate that yourself. So how does DSTE, how are we using FreeFlyer now? Well, DSTE has been primarily using the circular restricted three-body problem for most of its analysis in the past. If you don't know what that is, a quick go over of CR3BP, circular restricted three-body, is you assume you've only got three bodies, one big body like the Earth, one smaller body like the Moon, and then your satellite or your spacecraft. And it assumes that the middle body, your Moon, is always going in a perfect circle around the Earth. Of course, this isn't limited to the Earth-Moon system. You could use any bodies, but just for our example. And it assumes a point mass for a force model for both of your celestial bodies. So this is great for trajectory design, but it is limited when it comes to actually transferring this to the real world. And previously with DSTE, that was entirely the analyst's responsibility, is DSTE could be used to generate these trajectories in the circular restricted three-body, but then it was the analyst's responsibility to bring that up into higher fidelity models that are going to more accurately represent what you see in the real world. And we wanted to close that gap a lot. And so we've incorporated FreeFlyer into DSTE, and in particular, we have a mission plan that we've designed that is designed to take this trajectory in the circular restricted three-body problem, modify it slightly, but not enough to change the actual identity of the orbit, and then set that into a higher fidelity model, and in particular give you a FreeFlyer ephemeris, which you can then take out, and you can take that FreeFlyer ephemeris and go do much more complicated analyses using FreeFlyer and whatever powerful tool it is you're using there. And not only that, we have that one mission plan that we've created that DSTE goes directly into, but we've also built a kind of robust layer of code between DSTE and FreeFlyer so that it's going to be very easy for us to add more FreeFlyer functionality to DSTE in the future. And of course, FreeFlyer is only necessary for that step of going from our circular restricted three-body problem into higher fidelity models. But that's an incredibly powerful step. And so this is a really cool feature that we're really glad to have added into DSTE. So I certainly can take a bunch of pretty pictures of DSTE, and I have and will continue to do so in the future. But for now, I want to show it off in terms of what can we actually accomplish with it in the span of 10 minutes. Welcome to DSTE. This is the application. Just as soon as you open it, this is the main menu. And as you can see, we have a variety of tools to choose from here. Don't think of each one as like a different design path that you can go down. A lot of them end up feeding into one another. So our libration families tool is going to generate orbits around the Lagrange points. And then those orbits we can feed into the trajectory 3D viewer and interact with them. The create maps tool creates Poincare maps, which then you can interact with in the Poincare map viewer. Unfortunately, we're not going to have time to go through each of the tools today. So we've got a couple we're going to focus on. In a previous demonstration I've done of our two-level targeter in the FreeFlyer integration, we already had a trajectory ready, and we just plopped it in and we fed it through the targeter. And that's great, but I wanted to kind of show a beginning to end analysis you could do in DSTE. So what's our problem? We're going to keep it pretty simple for today, but let's say you want to design a trajectory around the moon that's going to be ideal for maybe photographing the south pole of the moon. So you're going to want it to be repeatable. You're going to want to spend most of your time in the orbit over the south pole. And of course, we don't just want to find that orbit, we want to take that orbit, and then maybe we want to create a FreeFlyer ephemeris, and then in FreeFlyer later we can go and do like a visibility analysis or something. So let's go ahead, let's pop into our libration families tool here. Oopsie. And as you can see in DSTE, we've got our Earth and our Moon here. I could change our bodies, but we're going to stick with Earth Moon now. And we've also got our 5 Lagrange points, 1, 2, 3, 4, 5. And how this tool works is we have a variety of orbits that we have preset around each Lagrange point, and orbits of different type too. So we've got a halo orbit around Lagrange point 1 or Lagrange point 2. But a halo orbit is not going to be particularly effective at looking at the south pole of the moon. So we're going to look at our near rectilinear halo orbit here. And what DSTE is going to do here in just a sec is it's going to take this preset orbit that we've already put into the application, and then it's going to modify it slightly, a lot. It's going to continue to do that, and it's going to generate about 40 orbits that will be generally similar to this one, but also different. So I'm just going to hit our little export button here. Oopsie. And this is just going to be the settings we're using to create this. Oopsie. There we go. And as you can see, just like that, we've created 40 different orbits of a similar type. There we go. And one of the really powerful things about this is if you ask me right now, Nate, can you go and plot me an NRHO? Can you tell me the starting state of it or anything? I couldn't do that in 5 minutes, but here in DSTE, we've done it for 40 orbits very easily. And we can come in and explore these orbits too. So if I click on this little selected trajectories tab, we have all of our orbits here, each is an individual one. And I can just go ahead and tell you that this one in the top left corner here is our most circular with the highest periapsis here. The one in the bottom corner here is going to be the one with the lowest periapsis, which will be this red guy here. I'm going to go ahead and clear our orbits from this visualization here. We'll just bring in this red guy to look at him here. This guy has the lowest periapsis. Our moon model is scaled up, so this trajectory doesn't actually intersect the moon. But as you can see, it's got a very low periapsis, and we're gonna try and work with something maybe a little less with a little less severe of a small periapsis. We're gonna drag this guy in, we've got this little green orbit here, green trajectory. And we're going to take this and we're going to create a higher fidelity ephemeris out of it. So I'm just going to go pull up this menu here. And I know this is not quite as fun to look at as our rainbow colored orbits, but it's a little important, so we have to talk about it. So on this bottom half of the menu here, we've got what we call our patch points, which are just like non-unitless states. There we go. So we've got XYZ and XYZ velocity, and then a time. And we've got one for each point that was generated for that trajectory, but we're actually filtering it down a lot. So we're only considering 1 out of every 10 patch points, which is going to both increase the speed and generally increase the ability to converge of our targeter. So this is an important little tool to play with, and we're going to play with our consider every number later in terms of getting an orbit to converge. And we've also got our number of revs. So right now, these states represent 1 revolution around this orbit. But if we wanted to increase that so we could have repeated revolutions, we could crank this up. We're going to leave it at 1 for now. Another important thing to consider is that in the circular restricted 3-body problem, the Earth and the Moon are always the same distance away from one another. Oopsie. But in the real world, that changes over time. So we're going to pick the start of our mission, which apparently our South Pole lunar viewing mission is going to start at New Year's of 2025. And last but not least, we're going to be kicking out that ephemeris. So we need to save that ephemeris somewhere. I've already got an FreeFlyer ephem ready to overwrite, so we're going to overwrite that guy. And I'm going to click generate ephemeris, and this is going to feed these patch points into that targeter. So everything I've shown you up to now has been entirely in Java, but those of you FreeFlyer users out there might recognize this as a FreeFlyer console. We are directly porting the outputs of FreeFlyer into DSTE here. And it's not just limited to our console, as we can see in just a sec. We also have visualizations. There we go. So if I zoom in here, so this is showing our propagated orbit, and it's also showing an estimation of our patch points in the little yellow squares. And I say an estimation because, like I said, as we've taken this from the circular restricted 3-body problem, we've had to modify it slightly in order to get it to actually converge on a valid trajectory in this higher fidelity model. But as you can see, if we take this, we've still conserved the identity of this trajectory. This is still clearly the same trajectory, even though it has been slightly modified, that's what's really cool about this tool. So I'll give you a quick top-level explanation of what's going on with our 2-level targeter here. So in the first level, what we do is we take each patch point, we step it forward in time to where it should be at the next patch point, because each of them have a time. And we see how close it is to the next patch point's position. And obviously, since we've just changed our models, it's not going to be exactly there. We give it a value based upon how far it is, and we do that for all of the patch points, and then we modify them slightly so that they arrive, so that when you step them forward in time, they arrive closer to the next patch point. And the overall value of all the patch points, which is just kind of an arbitrary number, but is output here, and this is the first level of the targeter. And as you can see, it's getting lower and lower. And then once it's quite low in that value, that indicates that most of the patch points are arriving very near the next patch point when they're stepped forward in time. But it's not just important that they arrive near the next patch point. They also need to have a velocity continuity. They need to be going the same speed as the next patch point when they get there. And that's what our second level is, which is our green one here. So our two levels, unfortunately, they kind of fight each other, because once you get position continuity, that generally gets rid of your velocity continuity. Once you get your velocity continuity, that generally resets your position continuity. And they have to go back and forth and tussle with each other. But in the long run, if the trajectory converges, then you get both of them to the lower point, at which point you simply take the trajectory, put it to the first patch point, step it forward in time, and then that's your output ephemeris. Okay, so our boss wants us to come and create an ephemeris that can view the south pole of the moon. But the other point that we talked about was that we wanted it to be repeatable. So what we can do in this tool is we can crank up the number of revolutions. And unfortunately, even though all of these orbits can be generated in a circular restricted three-body, not all of them are stable long-term within a higher fidelity model. So not all of them will actually successfully converge like that one did, even for one revolution for some of them. So let's take this guy in. We'll drag and drop him. That's this yellow one here, with a periapsis slightly farther from the moon. Let's take this guy, and we're going to do the same process. We'll overwrite our previous file, and we'll go ahead and set it for the same time. But let's go ahead and give it multiple revs. And I'll also increase this number, so we're only considering 1 in every 15 patch points, so we're considering some less, which will hopefully speed up our process a little bit. And I'll click Generate Ephemeris here. And so it's kicked off, and it is feeding through the two-level targeter. As we can see, our second level of the targeter, it generally we want to see it reducing in value. Occasionally it's going to bump back up, but hopefully long term it is dropping. So we've started with 5.5-ish e to the -1, and now we're at 6.3 e to the -5, so that's good. And our trajectory is converged here. Let's see. There we go. And let's go ahead and see our visualization. Again, showing it's showing the original patch points in yellow, or not the original, I guess it has modified them slightly. So the slightly altered patch points in yellow. But like we said, we've got multiple revs here. So it's going to go ahead and continue to perform the second rev. And as you can see, once again, although the orbit has been slightly altered, it is still maintaining the identity of the same trajectory. We are still having an orbit that is going to be spending most of its time in the southern hemisphere of the moon. And as we can see, although the orbit is not following exactly the same path, it is functionally a repeating orbit here. We have not destabilized and left the orbit or anything of that kind. And let's see, we should be just about to finish our third revolution. And there we go. And ephemeris generation complete. So we've also created that ephemeris, which again is in that higher fidelity model. So now we can take this ephemeris with multiple different revolutions at a specified time, and we can do much more complicated analyses with it. Potentially using FreeFlyer, potentially using other tools. So that's just, oopsie, pardon me here. So that's just one of the many things you can do in DSTE. Again, our little 10-minute presentation here. But one of the things we talked about is we have this robust layer that interacts with FreeFlyer, and we're planning on adding more functionality in the future. So we have a bunch of cool things planned. The current thing we're working on is this ballistic lunar transfer design, which is going to be using the 4-body model, using adding in the sun's gravity as well, to see if we can essentially create a perhaps save delta V by sending a slower transfer, maybe of cargo that doesn't need life support, from Earth to another lunar orbit. And so we're going to need another version of this two-level targeter to work with that four-body problem. Or similarly, heliocentric deployment, again using all four bodies, Sun, Earth, Moon, and your spacecraft, to be able to, say, deploy things from an orbit around the Moon, say for the gateway. You want to deploy it and make sure it's not going to come back and impact the gateway. And maybe you want to send it all the way out into heliocentric space where it's not going to interact with the gateway or any other future Earth missions. And our big long-term goal is to have a low thrust trajectory, where instead of our patch points having to be modified to fit into this higher fidelity model, we can perform small maneuvers or continually low thrust maneuver to keep them on an actual repeating orbit.
A couple questions about patch points. The first one, are the locations of those patch points automatically determined? Can you manually adjust them in any way?
That is an excellent question. So you cannot manually adjust the actual position of the patch points once you've converted from a trajectory into a patch point model, because you would be essentially changing the trajectory. But one of the features we're working on right now is the ability to change which patch points are determined to fit, to be sent into the targeter. So if we're considering 1 out of every 5 patch points, instead of sending patch points 1, 6, 11, 16 in, where you're considering only every 5th one, maybe you decide that patch point 4 is more important, and so you can manually change which one you're sending in. So instead of sending 1, 6, 11, you send in 1, 4, 11, or something like that. That's functionality that doesn't exist in our current release, but that we are currently working on right now.
Gotcha. And the last question about those patch points, obviously you showed FreeFlyer just kind of popping up, but how do the patch points actually get from DSTE software to FreeFlyer? How does that work?
So we are porting the patch points directly into JSON and then interacting with FreeFlyer with FreeFlyer's real-time API, which is very easy for us to pull up FreeFlyer from within DSTE, and FreeFlyer is more than capable of handling a JSON data interaction.
Gotcha. All right, well, we look forward to hearing from you again. When those new features are in DSTE, we'll bring you back up, hopefully later this year. And thank you so much.